So you have to have, in addition, CP violation to require that the decay rate of this is unequal to the decay rate of that, and the similar rate, right? So therefore, the total decay rate of matter and the antimatter are different in your lab with asymmetry. Yeah. So you have to have both C violation and CP violation. And, so click on this one. Yeah, and then to activate it, right? I don't know if okay, all right. Okay, so yeah, so somehow you have more matter than any matter. You have a left-handed universe rather than right-handed universe. By the way, the matter excess is 1 out of a billion. So 1 proton per billion photons, if you will. Yeah. Now I don't have a slide for weak interaction. We know that CP is violent in the weak interaction, but the amount of CP violation in the weak interaction is far too small to explain the matter and matter asymmetry. It's like 10 orders of magnitude difference, and this is due to the electric weak symmetry breaking, that you have different masses for the quarks, and once you have different masses, the effect on matter antimatter asymmetry from weak interaction CP violation is just reduced by many orders. So you have to have CP violation in strong interaction in order to explain the matter antimatter asymmetry of the universe. And we believe that the term that is responsible for CP violation is this T-Hooft vacuum pseudoscalar density of the gluon field. And this term is, is equivalently the color electric field dot the color magnetic field, and that's intrinsically CP intrinsically violates CP symmetry. And I'm not a theorist, so I don't know why it is so, but the classical analogy that I have, which is certainly wrong, but it's good a way to think about it, is that if you have if you have a left-handed particle in the magnetic field, the spin is aligned with the magnetic field, and if you apply electric field along the direction of the magnetic field, you are able to flip the momentum of the particle, so the particle becomes right-handed. So left-handed and right-handed are not conserved. You can convert between the two, and therefore you have symmetry breaking. This is sometimes called the topological charge. It's a quantum number, and this means that this vacuum density can fluctuate in such a way that you can have non-zero topological charge, meaning that the number of left-handed quarks and right-handed quarks can be different. Okay? And this is all from vacuum fluctuation. Yes, Uri.
I mean, this is not enough to explain the baryon asymmetry of the universe unless you have strong out of equilibrium behavior.
Yes.
But the quark-hadron phase transition is believed not to be of first order, and so it's very hard to get any out of equilibrium behavior on the time scales that the universe evolves. So I don't think I agree with you when you say this is what we need to have in order to explain the baryon number symmetry. It won't help.
Okay, fair enough. So I don't really know that whether this would be the answer, but if you have if you have to have CP violation in the strong interaction, this is a possibility.
Yeah, you may have that, but even if you do, it won't help.
Okay, so if you even if you do this may not explain the matter and the matter asymmetry, it could be something else. Yeah. All right. So you can have vacuum fluctuation and at high temperature. In the early universe, you can have different fluctuations in different vacuum states, and the topological charges are different, and you can really easily move from one vacuum state to the other. So they are kind of topologically protected. With that, now you have to have superposition of many vacuum states for your physical vacuum. And with that, you will have Hopf-free effect from vacuum fluctuation into other topological charge states. All right, so one of the effects is the so-called chiromagnetic effect that normally under normal condition you have, say, left, right handed balanced and everything is chaotic. Now if you have, so this is kind of a normal vacuum state with topological charge 0. And if you have fluctuation into non-zero topological charge state, say, for example, topological charge 4, you have more right-handed quarks than left-handed quarks. They're still kind of randomly oriented, but you have finite non-zero handedness in the domain. Now, in order to observe that, you have to have one way to observe that is to apply a strong magnetic field. So you align all the spins together, and once you align the spin together, then the momentum is automatically applied because they're along the spin direction. And if you have it, you have cancellation here that they are, most of them are random, and you're left with 4 right-handed quarks. And since the momentum and the spin are in the same direction for the right-handed quarks, now because they are different charge, their momentum, their magnetic moments are different signs. Therefore, they are oriented in opposite direction around the magnetic field. So you can have charge suppression. Positive charge moving in one direction, the negative charge moving in the opposite direction. Okay, and with that, you can have observable in the final state to see suppression of the pions, for instance. Now, how strong is the neat magnetic field in order for this to be observable? We know that it has to be very strong, but how strong? The back of envelope estimate would be that if I want them to be locked along the magnetic field. So the thermal momentum or the thermal temperature is irrelevant. So you want the energy scale due to the magnetic field to be a lot larger than the temperature. Say you need that to be 1 GeV. Then you would need a magnetic field on the order of 10 to 13 power Tesla. And that's what we believe that that we have in heavy ion collisions, because do a simple back of envelope calculation at 200 GeV, if you collide heavy ion and do just a classical calculation, you can get a peak magnetic field on the order of 10 to the 15 Tesla. So there is no problem that you can get a very strong magnetic field. The real question is really that the time evolution of the magnetic field, because this happens very quickly, and then the magnetic field can die quickly, and if it dies quickly, you won't be able to see the effect due to the magnetic field. So nobody really knows how the magnetic field evolves in heavy ion collision. And people say that if you have strong electric conductivity in the Wang plasma that you create in heavy ion collision, then the magnetic field can last for a long time, several Fermi over C, and if you have that, then you should be able to see the effect of magnetic field. Okay, just to compare the strongest magnetic field in the universe that we know, it's several orders higher. If you have a strong magnetic field that live long enough, will that be able to explain matter-antimatter asymmetry? And Woody told me that it's irrelevant. I don't know, but I don't know the answer to this question. Suppose we do observe charge suppression, and we do convince ourselves that that charge suppression is due to this color magnetic effect. How strong the color magnetic effect needs to be in order to explain the CP violation that is responsible for matter-antimatter asymmetry? I don't have an answer to that. I asked many people, many theorists who is doing this work on color magnetic effect that can give me a straight answer. So what? Yeah.
The situation in NBI collisions is very different from the universe because the expansion rate is about 18 orders of magnitude faster in NBI collisions. So the same strength of the CP violating effects can manifest in much larger effects because of the much larger out of equilibrium. So it does make sense to search for this effect in NBI collisions, even if it's not responsible for the universe and the symmetry.
So you're saying that it's possible that you may have it in heavy ion collision, but it has nothing to do with the of the early universe.
In the early universe, everything gets washed out by the slow, gradual transition through the phase.
Okay. So you're saying the early universe, everything is in equilibrium because it's slow.
It's the most perfect equilibrium.
But you got to have some non-equilibrium at the beginning, right? In the very early universe, but that's very early.
But not at 10 microseconds when the confinement transition happens.
Okay.
If people look at baryon violating effects at 10 to the minus 40 seconds, not at 10 microseconds.
Okay, fair enough. If I ask the same question to Dima, he would say otherwise. But yeah, all right. But take it as it may.
So go back.
Yep.
So the magnetar is still pretty strong magnetic field. Is there like some observational consequence? Like, you know, there's a lot of stuff creating around the magnetar, right? And will you actually observe, you know, okay, the length scale is much bigger, but suppose you have some fluctuation in the QCD vacuum in some finite temperature, would that also lead to some separation effect? Maybe the scale is too big, okay, but the fluctuation typically is local, right? But are there something you can observe in, you know, like if you, let's say if you are close to magnetar, do you see some kind of charge separation effect?
I don't know, but you observe photons basically from those. So
yeah,
from on the Earth.
On Earth, yeah. But if you, in principle, those are baryonic matter, right? I mean, it's
my guess is that no. No.
Well, it's just a fact of for order magnitude smaller.
Yeah, but it's not it's not on quark level, and you're talking about hadrons here. Yeah, my guess is not.
But inside the magnetar, you might have a Quark plus.
Okay. Yeah.
I had a question about you talked about the alignment to the strong magnetic field with the spins. I didn't understand the relaxation mechanism. So how does that process happen? How is energy being released to relax?
So if you have this vacuum state with non-zero topological charge, it's a gluon field, and the quarks interact with the gluon field. They have they flip the handedness of the quarks. So what do you mean release of the momentum?
Right. If I just have a spin and I have a magnetic field, it will start processing, right? So for it to align, it needs to relax. There needs to be some sort of dissipation. Yeah.
Well, this is the magnetic field is a normal electromagnetic field. and you have the quarks. I don't know. I don't have an answer to this question, but it's
Presumably from phonons or something.
presumably
From phonons or some sort of low energy excitation.
I don't know.
But this is a finite temperature, right? So
Still, you need to have conditions in order,
Yeah.
interactions of some sort in order to make the spin relax to the aligned state.
So there'll be some time scale for that.
Yes.
I have not thought about that.
But that time scale is probably strong interaction time scale.
Probably.
In order.
But the way I view it is that you have this vacuum state and you have ground field and you have quarks, and they kind of just automatically line up.
No, automatically they will recess. They don't line up. You have to have relaxation, you have to have dissipation for them to actually line up.
that's
It's
my
like when
question.
like when you put a ball in a bottle, it just keeps going like that. In order for it to settle down at the origin, you have to have friction.
But does the temperature provide that kind of excitation for them to?
Temperature by itself will not.
Because
If the temperature is defined only by interaction with some walls, but no interactions among constituents.
yeah, the thermal motion for the quarks and
Yeah,
gluons.
so you can say, because we know that the system behaves like a approximately thermalized fluid, there must be interactions that achieve that. But these interactions are brought with viscosity in a spin independent way, but here we need spin dependent aspect, the variation of that.
Right, but this is the for the vacuum. This is the color electromagnetic field. Yeah.
And now, I mean, we are talking about the alignment, as you said, of the spins with the external magnetic field.
Oh, okay, all right, right.
If you put a quark spin into the external magnetic field, it will just do that.
Mhm.
It's classical spin dynamics.
Okay, yeah.
So for it to align, you have to have some microscopic relaxation process. And I'm sure Chin-Feng and Kovacs have thought about that, but I don't know exactly.
Yeah, I asked them this question that so they have this model, I want to say, and they have an estimate of the magnitude of axial current. And they give a ridiculous large number, 10%. So this is the entropy density. So it's you have a 10% asymmetry in the left-handed, right-handed box. And if you have 10%, then you can end up with 1% effect in the final state, which would be observable. And that's their estimate. And they say that this is the best or the most probable estimate that they can have with the energy density of the quantum plasma.
So what? So what are the inputs there? Do they consider some like thermal effect, basically spiral transitions, and how much on average you can get away from zero?
I don't know. I asked this question that what is the probability for the spiral transition? Yeah, there's no clear answer about probability. Nobody really knows.
You cannot calculate, but I think that's always like you have a finite temperature, then you have spiral. I mean, I don't know if there's a dynamical model. I never hear there's a dynamical calculation. But
I originally thought that the temperature has to be as high as 1 GeV. But I asked people, and they say that a few hundred MeV would be probable. And we do have a few hundred MeV in QGP. So yeah, you can have probably 1 GeV in early stage of Hamilton collisions.
Well, I mean, the Speleron rate was calculated for the electroweak phase transition by Larry and friends 20 years ago. And there you can do it reliably because of the weakness of the interaction. And you can use the Clovis as well. that at least gives you an order of magnitude for the Fallon rate in QCD, but it's not a precise allocation.
Right, and that is the when GEV comes from, I guess,
I don't know.
in the temperature, in terms of temperature.
Oh, no.
Okay.
You mentioned one PV.
Okay, yeah, but that's the number that I have in my mind. Okay, good enough. So I do want to mention that there is CME observed in condensed matter, but this is really that if you have left-right asymmetry, then putting it in magnetic field, you will have the current, and that's well understood physics. It's really about the initial state, how you get the left-right asymmetry, and in condensed matter is just from the electromagnetic field, so they can make it. So that's not to me that's not a fundamental thing that you can make left-right asymmetry, and then of course you can have current at the end that you can observe. Our question is whether this is true in heavy ion collisions, whether you would have left-right asymmetry in your system, and that's the big question. Right? So this is kind of everything on a single slide, but I want to just emphasize that if you do observe chiromagnetic effect in heavy ion collision, that could be something very important. It may not relate to matter asymmetry, but still that's a fundamental question in QCD. Okay, so to measure the chiromagnetic effect, right? You have to create the early universe. You have to create a high temperature system. This is the signature of a chiromagnetic effect. So you have, positive particles in one direction and the negative particles in the opposite direction along the magnetic field. And the magnetic field is on average perpendicular to your impact parameter direction. So this is the reaction plane. So you have, collisions perpendicular to the screen. One is into and one is out of the screen. Seagate Voloshin came up with this observable, basically an angular correlation, a 3-point correlator. So you have two particles. These are the azimuth angles of the two particles with respect to the reaction plane that you can kind of reconstruct from final state particle distribution, or you can use a third particle in place of the reaction plane, and you do a 3-particle correlation. And then at the end of the day, you can extract this gamma correlator of 2 particles. This is the initial measurement. So you do have
What is the angular bracket?
This is the average of all pairs. So you
In a single event?
over all events. So in the single event and then over all events.
You average over all events, don't you average over all orientations of the reaction plane? Zero?
Yes, well, you do reconstruct the reaction plane event by event.
Okay.
So yeah, with respect to the reaction plane of that particular event, and then you average over all events. This is the early measurements. You do observe large separation between unlike sign and like sign. Okay, and it's all out of 10, a few times 10 to the minus 4, which means that the asymmetry is on the order of a few percent, and that's a big effect. But actually, we know that this is mainly due to background. So what is the background? Background is so just going through the cartoon. The CME, the chiromagnetic effect, will give you the gamma correlator to be positive for unlike sign pairs and negative for same sign pairs, and they are symmetric. Okay, one is positive, one is negative, and we do have momentum conservation, which is back to back, right? So you have all the pairs to be. You have a preference of back-to-back correlation for all pairs regardless of the charges. Therefore, you should have a kind of constant overall common shift for all pairs. And you still have suppression between the two. Okay, so we can measure the difference between the two, and that difference would be insensitive to the momentum conservation effect. And so that's fine. But the problem is really due to those kind of resonance decays, for instance, that those neutral resonance decay will create correlation between unlike sign pairs. And we have a lot of those, and they do not affect the same sign pairs, but they pull up the unlike sign, the opposite sign pairs. So you have a bigger suppression between the two. So you measure a suppression, and now you don't know whether that suppression is due to those background or due to the color magnetic effect. And this is really now depending on the relative strength of the two effects. And you can, this is a measurement, and you can kind of see, pattern like this, right? And now we're interested in the difference, but the difference is still contaminated by this piece of background. So at the end of the day, what you measure is going to be something like this. So you take the difference between opposite sign and the same sign. This is called delta gamma, and this is the CME signal. So that's what you're looking for. And you have a background, and this is due to, say, a row decay into 2 pions. So it's proportional to the number of rows, inversely proportional to the number of pairs, of course. And then this is the decay angular correlation. And it's proportional to the V2 parameter of the resonances, because we are talking about the reaction plane dependent correlation. So this is the V2 effect. So the background is going to be proportional to V2 divided by the multiplicity, because this is one end and these 2 ends here. Okay, you can do estimates from models, and or back of envelope estimate. First of all, you can get a value of something like 10 to the minus 4, and that's the same order of your measurement. Okay, so you start to feel that that's a problem, and actually a more rigorous, still model dependent estimate. You use a model, so-called brass wave model, initially from Uli, that describe all the spectral, the bulk properties of the collision. You extract parameters, and then you plug that in and calculate the correlator, and you get things like this that the brass wave model can describe entirely, if not entirely, more than 90% of the signal that you measure. Okay, so and that's the problem. And so now you start to think about how to deal with the background, right? If the background is small, then you don't worry too much. But if the background is big, then you really have to deal with the background. And the background is going to be proportional to the elliptic flow parameter. So the first thing that we thought about is that just look at this signal as a function of the V2 parameter of your particles in your event. This is the so-called event shape, and I should speed up. I think that this is mainly due to statistical fluctuation, but you still see a very linear, nice relationship, and this tells you that there is a huge background there. But initially we thought that this intercept would be the CME signal. Okay, but actually it turns out that there is still a contamination from background, and this is because that we do event by event selection of the final state event shape, and that does not necessarily mean that your background elliptic flow is 0. And from model studies, we do see that at this 0 event shape parameter, you do have finite positive V2 of the low resonance. So you still have a residual background. So So this way we can really kind of pin down the CME. You can do another way by looking at the V2 of this entire event, but now your V2 is actually, or your events are selected by the V2 parameter in forward direction. And then you look at particles in the middle rapidity region. And then you look at this variable, this measurement of delta gamma as a function of V2. And in different centralities and different selections of the event shape in the forwarded region. You put all the points on the graph and you see a linear dependence. And now you want to extrapolate this to 0. And once you do that, you get a consistent with 0 intercept, which means that if there's CME signal, right now the statistics are not good enough to pin down the CME signal.
Question. So what is the expected energy dependence of the CME? Let's see, compare the same system at the weekend LHC.
Theorists told me that at high energy, or RIC is the sweetest point. At high energy, you can have stronger magnetic field. The magnetic field dies more quickly. So they're competing effects. They said that RIC for energy would be probably the best place to look for the kind of magnetic effect. Yeah. So at LHC, you may not expect a stronger signal.
The signal is smaller, might be smaller, but your ability to control background is better because you produce many more particles in the same size, right?
Yes. So the background seems to be similar between the two energies. So that's something that the reason I think is because as you said, that at the high energy you have more particles and therefore the background is diluted more. But turns out that the background strength are similar between the two energies. And I think this is because that you have more low production. Or other higher mass resonance. So actually the ratio is the same, similar between the two energies. You can look at the embedded mass of the signal. So you look at delta gamma as a function of the embedded mass of the pairs. And these are the resonance. So you have a residual background due to correlations in the event. On top of that, you have resonances, and you see the delta gamma has similar shape, which means that the majority of the delta gamma is from those resonances or from the correlations in the event. Okay, and I will skip the details. We did upper limit estimate, and it's 15% CME signal that you can have at 95% confidence level. You have large delta gamma measurement in small systems, in proton lead collisions, in proton gold collisions, neutron gold collisions, and this tells you that the majority of the delta gamma is background, because you do not expect CME in small systems. But the delta gamma are very similar between small systems and the large systems at both energies. Again, tells you that 90% of the signal is probably due to resonance decay as background. So initially people hoped that, we knew that there was background. We just didn't think that background was that big. Okay, and if the background is really big, then you really have to nail that down experimentally. You can't rely on theoretical estimate using models and so forth. And therefore, we come to comparative measurements, and one of the comparative measurements is the Isobar collisions. Okay, so with ruthenium versus zirconium, you have the same mass number, and that gives you the same background, naively speaking, and you have different atomic number, different Z, therefore different magnetic field, different magnitudes for the CME. So now you can distinguish between background and the signal. This was a fantastic idea, except that you can get really identical nuclei. So estimate, you have, so this was an early estimate, and we did have 2 billion events each for the 2 systems. And therefore this significance should be, so the estimate was 400 million, so square root 5. And so this is kind of the signal significance as a function of background level. Okay, if you have 10% signal or 90% is background, then with this amount of data, you should expect times square root 5, you should expect 4 sigma effect. Okay, if the signal is 10%, and you can really kind of do it on the back of envelope. You will get with this amount of data, you will get statistical precision of 0.4% in terms of your comparison between the 2 isobars. And if your signal is 10%, and the magnetic field strength difference between 2 systems is about 10%, and the signal is proportional to magnetic field squared, model calculation tells us that the effect would be 15%. So a 10% signal, and we expect maximum 15% between the 2 systems. So we expected 1.5% difference between 2 systems, and that's big enough compared to the statistical uncertainty. We do have to control the systematics, and that's why we actually did extra effort to make sure that we have the same systematics in the 2 systems. We alternate in the beams frequently. So we did control the systematics to a very good level. And this is the measurement. So this is the outcome of the Isobar data. And just look at the breakpoints. And this is the delta gamma over V2 ratio between the 2 systems. Okay. Delta gamma is the measurement, is the observable, and we do normalize it by V2 because we expect the background to be proportional to V2, so we get rid of that. And if the background is the same, proportional to V2, but other than that, everything is identical, then all those points should be above 1 if we have signal. And this was very strange that it's 3% lower than 1. Okay. We actually instantly knew that was due to multiplicity difference. Yeah. The 2 systems are different, even though the A number is the same, but the nuclear structures are different, and therefore you expect difference. And so again, this is the delta gamma over V2 measurement between the 2 systems, and now this is as a function of centrality. And this would be the background. The V2 is taken care of by the ratio there, but there is this prefactor, okay? And this is inversely proportional to multiplicity. And if your multiplicities are different, then you automatically get a difference. And the multiplicities are very different, actually more different than one would expect, a few percent. If you inverse that, you see the same shape, right? Identical, and this this wiggle is not really something due to physics, but due to our centrality definition, not precisely like 5%. So this is understood, just technical. But even with that, you see the shape in the delta gamma over V2. That tells you that almost 100% is background. So the better variable would be multiplied by the multiplicity. Then you would get the baseline to be 1. Why the multiplicity are so different? And this is because the two nuclei are different. They are of different sizes. And turns out that you do a nuclear structure calculation by DFT, you see that the ruthenium nucleus is a bit smaller than the zirconium because the zirconium has a thicker neutron thickness. And therefore, in ruthenium collision, you have slightly higher energy density. And therefore, you have slightly more multiplicity, larger multiplicity by a few percent. And actually, if you take the multiplicity, the ratio of the multiplicity distributions, you get something like this, the gray points. These are data. And actually, the DFT calculation with a global model or Trenton model for multiplicity production, you can predict the shape. Okay, and this tells me that actually the nuclear structure calculation is pretty good. It has the right ballpark effect here. By looking at this red shape is non-trivial. Actually, it's not flat. We have this kind of arch or a back bump, very wide over multiplicity, and then of course rising tail. And this is because the ruthenium collision has a slightly larger multiplicity, so you have a larger effect on the tail. And actually, you can use these to actually probe the nuclear structure. The V2, the elliptic flow, is also different. And this is because if you have different size, and now you have the same impact parameter, your overlap shapes are going to be slightly different. And that difference is on the order of a few percent, 2%. And that's also predicted by DFT calculation of the nuclear structure plus the geometry, global model geometry. And you actually predict that the V2 difference will be on the order of 2 to 3% with respect to the participant plane. And actually, if you measure the reaction plane, the difference is 10%. And it's also predicted. And the data actually tells you that it's more or less 10%. So the structure of the nucleus that is calculated is quite good. So back to the Isobar, CME search. So if everything is scaled by multiplicity, and actually Kazif, Liao, and Xi, they actually, assuming that things are inversely proportional to multiplicity, then this would be, so this point is the multiplicity ratio. And so this would be your baseline, okay? And all the data points are above that baseline. And a few sigma, okay? 3 sigma, and that's, that's possibly a signal, right? But things are not that simple. Actually, here you see that this is a number of row or number of clusters. And this is not strictly proportional to multiplicity. Because if your energy density are different, then the higher the energy density, the more heavy mass resonances that are produced. So actually, you have more clusters than the multiplicity difference. And therefore, and you can kind of measure this using data, okay? By just looking at the number of opposite sign pairs minus the number of same sign pairs. And that's just, the correlated clusters. And this would be the ratio between the two systems. And that's, the difference between these two lines is about 1%. And that's all we measure, okay? So if the baseline is this line, then all your signal is negative. you don't have CME.
So it's the baseline doesn't seem to have a vertical error bar. How do you
Yeah.
get it that accurate?
All right. So now these are still naive expectation of the baseline. Now we did more, and I'm not even talking about the complications here. So you have the complications are the following. You have V2 measurement, and you have non-flow contributions in the V2 measurement, and you have to take care of that. And you also have 3 particle correlations that are not due to CME, like the diagens, for instance. You can have many particle correlations, and that contaminates your delta gamma measurement. Take care of all of those. This would be our. This is still preliminary. Okay. This band now we have error bars here, and these are our estimate of the baseline. So right now we don't have a signal. The signal is consistent with 0. All we can do is to extract an upper limit. Okay? We're not there yet, but my upper limit would be 10% at 98% confidence level for the CME. Let me continue with a few more minutes. We can, so instead of Isobar, you actually have another, actually I would say better measurement to compare. And this is just use the same event, but reconstruct 2 event planes. One is the participant plane, and the other one is the reaction plane, or the spectator plane. And due to geometry fluctuation, they are different. And the good thing is that the magnetic field is.
Sorry,
yeah.
What's usually called the reaction plane is not the spectator plane.
Yes, you're right. Yeah. And the spectator plane and the reaction plane are very close to each other from global model. Yeah, they're almost identical as far as I can tell from global model from geometry.
There are no plane fluctuations.
There must be, but it's very small. So we have big fluctuation between participant plane and the reaction plane. The opening angle is big, and for spectator plane and the reaction plane, the opening angle is very small.
Why is that?
I think
Geometry.
Yeah, I think it makes sense. They are kind of complementary. So
yeah, so that's what I would have also thought. That means if one is uncertain, the other should also be uncertain.
yes, but they are closely correlated. That's what,
Yeah, it's
we will discuss this after.
Yeah.
it's the participant plane or the reaction the interaction zone, that geometry, it depends on a lot of things, right? Not just geometry is one part, but you have the interaction, the fluctuation in the interaction gives you probably a large fluctuation.
Or I get you a comment. So you say if the reaction plane measured by something participating fluctuates relative to the participant plane, the spectator plane has to also fluctuate in exactly the same way.
Yes, that's how we understand.
That's impossible.
Huh?
That's impossible. I mean, the spectator has to have big widths. So I wonder what does it enclose.
The
The width is at 90 degrees or more. Nothing.
the width of what?
The width, if you were taking, I mean, so spectators will not depend on whether you low energy or not. I mean, their multiplicity stays the same.
Yeah.
The correlation between the plane, which you determine from spectators versus true plane, will have a width of the order of 90 degrees. So given the other, again, we may reduce 90 at fluctuations of doesn't matter, but 90 is in the bank.
Well, it's
You can get more.
your 90 degree is my 0 degree. So,
No.
oh, you mean with the opening?
He says the resolution, the event frame resolution from spectators is much worse than for participants.
Oh, the
because
resolution is taken care of, right? We correct for the resolution. So we're talking about the real, we're talking about the real theoretical plane.
I think it makes sense.
But a spectator in theoretical plane,
The spectator is the what we measure, we kind of measure spectator, right? We do not measure all the spectators. So that's the experimental resolution.
right?
We correct for that. Once we correct
You
for,
cannot correct something, you don't know whether it's. to
or we
the
do not
left or
get
to the right.
to, yeah, we do not get to theoretical plane event by event.
Yeah.
We do it on
Yeah.
average.
You
yes.
correctly event average.
Yes.
Oh, okay, so if they're close on the average, then I can agree, not that like that.
Oh, yeah, right, right, yeah, that's what I mean, yeah. So we have, so you can measure two planes, and because the magnetic field is more aligned with the spectator plane or perpendicular to that plane, you get more signal there. So actually, this is actually in the same event, you make two measurements. Just like, you have isobar measurements, but now in the same event, in the same nucleus. And therefore, the background would be identical. You don't have the difference between due to kind of issues that you have with isobars. And you can extract the CME fraction this way. And this, this is just the relative measurement of delta gamma with respect to these two planes. And of course, if this is 1, then you don't have signal. And if it's above 1, that means that you have signal. Okay. This is the results that we extracted. Okay, from gold-to-gold collisions. This is now gold-to-gold, 2 billion events. And this is the red points are medium central collision. And those 4 points are not independent. Those are 4 different ways to analyze the same data. Okay, so just pick 1 point. That would be your signal, and we have something like on the order of 2 sigma effect. Okay, and the blue points are peripheral collisions, and they are consistent with 0. Okay. So we have quote CME signal on the order of 2 sigma. Okay, in gold-to-gold collisions. Now this is, I said quote because this is still have contamination from background. And these are the non-flow that I talked about. Okay, I'm not even talking about details how to estimate non-flow, but yeah, I'll be almost done. Yeah. Actually, if this all kind of model estimate, and we can do that with data more, and it's ongoing right now. But actually, the background due to non-flow and 3-particle correlation, the net effect is maybe negative. Okay, so it's possible that indeed there might be some signal in the data. Of course, it's 2 sigma effect. Could be fluctuation. So we need more data, and we will have more data in a number of years. This is to tell you that actually isobar we see no signal, and the gold-to-gold we see a hint of signal, and they're not contradictory to each other. And this is because actually in isobar collision your signal is smaller by a factor of 3. That's my estimate. And this is because your magnetic field in isobar collisions is smaller because your N number is smaller, and your background, or the Z number is smaller. Yes, sorry. Because the N number is smaller. Yeah, it is Z number is smaller. And your background is bigger in isobar because your multiplicity is smaller. So your background is less diluted. And my estimate is factor of 3. And therefore, if you have just a couple of % signal in isobar, and our error bar 0.4% divided by 15%, that's 3%. So our error bar is 3%, and if your signal is a couple of percent, you're not going to see it in Isobar conditions. Okay. So I can probably skip this, right? Because this is now, the main purpose of this this program. You can actually, okay, good. You can actually turn it around, right? Now, isobar measurements can be made very precise because you are comparing two systems, and a lot of things cancel. And now your measurements is exclusively sensitive to nuclear structure. For example, that if you have and you're sensitive to the neutron skin thickness, so to speak, and neutron skin thickness is sensitive to the slope parameter, the L parameter in your symmetry energy. And if you can measure, the nuclear structure or the neutron skin thickness in isobar collisions, and you can infer the symmetry energy, L parameter. And that's actually what we did in STAR, and this is a preliminary data. You can look at the multiplicity difference, right? And this multiplicity difference will depend on the neutron thickness, because the neutron thickness tells you how different these two nuclei are, and that difference turns into the multiplicity difference at the end. We can extract a number with 50 some MeV for the L parameter, and the error bar dominated by systematics is about 10 MeV on that order, and that is the main systematics is from the nuclear deformation that we are not certain. We don't have a precise measurement yet, but if you put, these are the preliminary data from STAR, okay, in terms of the L parameter, and this is what data, and they are consistent, and we have actually comparable error bar now, and I think that's important because even though the error bars are not much better, they're at least comparable, but these measurements are very different from all other measurements. Right? This is just multiplicity differences in high energy collisions, very different systematics from all other measurements. So I think that's a real contribution. Yeah.
So how does the multiplicity tell the neutron from proton?
So you don't tell neutron from proton, but you tell. So this is sensitive to the overall nucleon density. So you do have to have model. You do have to have theory input. So
you test different, like for example, shell model calculation and test which one of that models.
Yeah.
Oh, okay.
Yeah. So at the end of the day, you get the nucleon density distribution, and that depends on the neutron thickness. Yeah.
So one comment. So this comparison, Isobar ratio is done using global model, right? Of course, you include the DFTs. The question will be how sensitive the tail of the multiplicity distribution depends on the final state dynamics. In others, the tails, any smearing, right? Mm-hmm. You will be sensitive, deformation, neutron skin, but also the particle production. I wonder what happens if you have a global plus hydrodynamics, and then with the same DFT input, and see whether the ratio depends on the final state in the tail region.
Yeah. We did different models, and you do get some variation from different models. So this is the physics governing the multiplicity production.
Sure.
So you do have some uncertainty from that, and that's not big.
I think we need to see the actual study.
Well, yeah, these are models right here, different models. and that's the range that you get. So you have let's see, these are models, and this is the range that you get basically. This bar is the range you get for the neutron thickness. Okay, and this is factored into here.
So the centrality range is different. Here 0 to 5%, then that one 0 to 2%.
Yeah, actually, it's not very sensitive to centrality because you take the ratio of two systems with the identical centrality. So whether you pick 2% or 5%, no much difference. Yeah.
But I remember for this particular plot, the argument is the tail, right? You want
Yeah.
to look at the tail,
Yeah.
and the 0 to 5% have smaller amount of the tail than 0 to 2%.
For here, for here you have the tail doesn't depend on the centrality. So no centrality definitions, just the tail. You look at the tail, right? Here we did the multiplicity ratio, and we kind of use 2%. And you can also use 5%. You will get different numbers, different value, but still that this number will be the same. It's that this number will be different, but all those curves will be different.
Right.
Yeah.
So, but if you take the right plot
Mhm.
and the neutron scan, let's say you have a uncertainty of let's say 0.18 plus minus 0.02. That range, I'm saying that range imply a symmetry energy probably bigger than what you quoted here. Right?
No,
Because
no.
I don't know. Maybe Wang.
I think it's smaller.
This range is, I don't know, this neutron scan there, you're changing.
Is that low C IP like 0.1 nuclear per cubic per meter? Low C. It's like 2/3 of normal density, right?
This is something like 2/3. They call crossing. This is from Lewin. And this is the saturation density.
Yeah. If your neutron scan uncertainty is 10%, what is the corresponding uncertainty on the L? You see the band there, that's 10%.
Okay, I mean, one has to use an extrapolation from some saturation density to normal density. That part is a little model dependent.
Okay. Yeah. So this number includes.
Okay.
So this number includes this and the symmetry, the deformation parameter. Yeah. And this is plotted in here. Okay. And from here to there, as Bowie said, that there might be some issues. Yeah. So that's right now what we have. I will skip this. This is the peripheral collision, very peripheral collision. We call Grazing isobar collisions, because the naive idea is that on the periphery, you're more sensitive to the neutron scheme, and therefore you have more sensitivity. But then the data, for those peripheral collisions, you don't have many events. Actually, the statistical precision may not be as good. But you can look at those events and study the neutron scheme. That's all I have. I will stop here.
There was a question in the chat.
Ask him to ask. Just ask him.
Okay, I'll ask. I'm remote, so this is Bill Lynch. So my question is, if you look at the P-Rex experiment and also the sensitivity in calculations, the skin thickness is sensitive more to the derivative of the symmetry energy at 0.1 nucleons per Fermi cube rather than 0.16. But you're quoting the value for 0.16, which makes it more sensitive, also sensitive to K-sim. So my question is, how do you know that this observable is sensitive to this derivative of the symmetry energy at 0.16 rather than 0.10?
So as Boyan said, that there is extrapolation involved. So we extract this symmetry energy at 0.10, I believe, and then we extrapolate that to 0.16.
Yeah, but that means that you have to make an assumption about K-sim.
Okay, yeah, I'm not familiar with that. Yeah, so
I think this extrapolation was done within the so-called extended Scrum hierarchy.
yes, yes.
And so that's in that model. The K-sim is within that model.
Okay.
I didn't really catch Bao, and I couldn't really hear you very clearly, so.
Okay, so this extrapolation from two-thirds normal density to normal density was done within the so-called extended Scrum hierarchy model by Levin Chen. In that model, the K-sim, everything, is determined by the model parameters. So that part is a little bit kind of model dependent. The K-sim, is within that model. So one has to go inside that model to look at what is the K-sim they use in that particular model.
Yeah, oftentimes the K-sim is negative, so that will decrease L. That is compared to if you have K-sim is basically 0, then it basically the value is more similar, but yeah.
And if I remember correctly, it's on the order like minus 150 to 200, I mean, K-sim.
Mhm.
Yeah, okay, I don't know that number. Yeah.
Okay, thank you.
I think later when Claudia gives talk, probably if we have more discussion on how this number extracted, will be useful, right?
Yeah.
To, maybe I suggest.
Yeah. What I know is that Lewin's model using the row C, and they extract this number, and this is other people using the saturation density directly.
Well, I actually, most of like the systematic you have shown, most people have shown that the neutron skin is sensitive to error at two-thirds time normalization, like what the Lewin is saying. But when people compare the models, they always quote the snowball symmetry energy at normal density as a parameter to label the model. But actually observe you're looking at is not determining the symmetry energy at normal density, but at two-thirds time, what you and Bill say.
Right. And you have extrapolation from row C to row.
Right.
And everybody has that extrapolation.
Yes.
And that extrapolation is different between different people.
Right.
Okay.
Okay.
Yeah, I'm saying this Friday there's a talk that discuss all of the details. We need to maybe.
I'm not sure if those details will be discussed because the model calculation is done by Leo.
We can suggest him to do that. Right.
But that's so the extrapolation is is one particular extrapolation, I guess, from Leo. Yeah.
Yes.
And I don't know how big the uncertainty that is. You may know.
Yeah, I mean that's not like when we do high rank careers, people look at it for low.
Right.
You label your equation of state, use K-note, incompressibility and normal density. But your reaction, you say I did 100 T with probing the equation at this 4-5 times normal density. But you only label the K incompressibility at 2 and 4 times normal density, but you use the number
You have
normal density to label your equation of state. That's the same situation.
Okay, yeah.
Do you have the UPC event reporting for Isobar collisions? The UPC events, like if.
I don't think we have a UPC trigger.
Oh. Okay.
So we don't have enough events.
Yeah, the events are biased, but then you can still get some UPC information, but it's not it's mixed with the you have to do some kind of cleanup, but you missed most of the first section, but there was no trigger. But we don't have UPC trigger, but we still have a UPC events, but it's not.
And we don't have.
Why you ask this question?
Because the proton distribution are different. The photon, they call it photon velocity.
Oh yeah.
I know.
You have some measurements.
So there's in quantum method there are results shown. There's some results showing that indeed you are sensitive to the charge difference in the light by light
That would be too
Yeah,
far apart. It's just like
like the meson production.
yeah, any cross section. Photon by photon would be too small in cross section.
Yeah. Measure.
Yeah, like define any process that can trigger on select whatever have the largest cross section. And use that.
You want to study what process, like photonuclear?
Yeah, yeah, something like that. Because in this case, the photon luminosity.
I think we do have some measurements.
We do have,
Yeah.
but it's the trigger is biased.
Yeah.
But we do have.